To this 20-second lecture on calculus of variations. In this lecture, what we are going to do is we are going to see the finite variational problems with finite subsidiary conditions. In the last lecture, what we have seen is we have seen how to extremize the functional of the form this when the admissible function y is such that some other functional has a fixed value, say L, right? These problems were called isoperimetric problems, and we have seen how to solve those problems. And this condition is called subsidiary condition. This condition is called subsidiary condition, and this problem was called isoperimetric problem. And in this video, we will consider finite subsidiary condition. What is finite subsidiary condition? Uh, Basically, what we want to look at is, suppose this is a functional, which is a function of n variables, n functions. So basically we have y1, y2, yn as our input functions, right? And we are looking for an extremal of this functional subject to these boundary conditions and these subsidiary conditions. What are the subsidiary conditions now? Here the subsidiary condition was in the form of a functional, right? We wanted this functional to be constant, but here the subsidiary conditions are simply functions. We want that our y1, y2, yn should be such that they satisfy these k equations. Okay, these n functions should satisfy these k equations. So basically, simple thing is that we are looking for an extremal of this functional which satisfy these boundary conditions, but the admissible curves, these admissible functions y1, y2, yn should be in the n minus k dimensional space defined by this double star. So basically we know that if we have this we have this y1, y2, yn as our variables, these are the input functions, right? And these satisfy k conditions, right? So it means that we are in a n minus k dimensional space, right? So basically, if you don't understand this thing, it's okay. Just we are looking for a extremal of this functional which satisfy these boundary conditions and these n separate conditions. So you can see these are simple algebraic conditions. Okay, simple. For example, we want y1 square plus y2 square is equal to 1, y1 square plus y3 square is equal to minus x. So these conditions are like these conditions. So these are called finite subsidiary conditions, and this was our subsidiary condition which we have considered in the last video. So if your condition is a subsidiary condition, then you classify that problem as a isoperimetric problem, right? So these problems, we don't call these problems as isoperimetric problems. So how to deal with these problems, let us see. Okay, so let us define our problem. Basically this is a theorem. This theorem, for simplicity, I am taking only n is equal to 2, that is I am considering only y1 and y2. I am calling that y1 and y2 as y and z. Okay, so suppose and k is equal to 1, it means that there is only one finite subsidiary condition. Okay, you can always generalize these things. Okay, so my problem is, suppose I have this functional which depends on two input functions, that is y and z, and let the admissible curves, they satisfy this condition. Admissible curves y and z. Okay, admissible curve, what an admissible curve will look like: y is equal to y of x, z is equal to z of x. Actually this is a curve in 3D. Okay, right? And we are saying that suppose this curve lies on this surface, right? For example, suppose we want to find a curve on the sphere such that length is minimum joining 2 points, right? Then this problem can be categorized like this, right? We have already solved these problems. These are geodesic problem, but we can consider that problem in a different point of view, that is here. Like we can consider that we are looking for the curve y is equal to y of x, z is equal to z of x. This is a curve in 3D, right? Such that curve is always on the sphere, right? This is like this. The curve is always satisfying one condition, right? And these are the boundary conditions. Okay, so basically we want to find out the extremal of this functional such that this curve, which is a curve in 3D, always lie on this surface g x y z is equal to 0. This is a surface, right? And satisfy these boundary conditions. Okay, so we have this theorem which says that suppose this functional has this extreme, this curve as its extremal, right? And suppose g of y, that g of y means partial derivative of g with respect to y and partial derivative of g with respect to z, do not vanish simultaneously at any point of the surface star, right? This is how we are choosing our surface. That surface is not such that at any point these two things are zero simultaneously. Suppose our surface is of that kind, it means that these things are valid only for surface of those kinds. Then we claim that there exists a function lambda x, right, such that this is an extremal of a new functional, which is this one, right. So basically we say that we know that how to write this is a function of x, y, z, y dash, z dash. So we know that how to write the Eilis equation for this. The Eilis equation, suppose this is your capital phi, then Eilis equation is phi y minus dy by dx of phi y dash is equal to 0 and phi z minus dy by dx of phi z dash is equal to 0. Now phi y will be fy plus lambda x into gy. This is this thing minus dy by dx of, there is no y dash in this. G is simple algebraic x, y, z. So it will be simply fy dash, right? Similarly, phi z will be fz plus lambda gz minus dy by dx of, there is no z dash in this g, therefore it will be fz dash is equal to 0. So these are the two Eilis equations. Okay, these are the Eilis equation which the extremal of this functional will satisfy. Okay, so in the last video we had if we have this f, we want to extremitize. We wanted to find the extremal of this functional, and the constraint was that integral g should be L, right? This was in the last video. Okay, and in this video we have this functional. We want to find the extreme value of this functional, and the constraint is algebraic constraint, right? Okay, 0 or something, like it can be any constant, right? Here the new functional was f plus lambda g, where lambda was a constant. In this case the new functional is f plus lambda x into g, where lambda is a function of x, right? This is the difference. So we have to prove this theorem. Let us prove this theorem. So we are given that we are having this x, y, z, y dash, z dash dx, and we are given that this curve, which is defined by y is equal to y of x, z is equal to z of x. We are given that this curve is an extremal of this, which satisfy the boundary conditions as well as this algebraic condition x, y, z is equal to 0, right? Okay, so what we are doing is, this is from a to b, so our interval is from a to b. We are choosing an arbitrary point x1 in this interval. Choose any arbitrary point x1 in the interval, and we are given that this is an extremal, right? And now give y of x an increment delta y and z of x an increment delta z. This delta y should be non-zero only in the neighborhood of x1, and this delta z should be non-zero only in the neighborhood of x1. So your delta y looks like this, and delta z looks like this, right? Then using the definition of variational derivatives, which we have seen in the second last video also, and in video 5 also, we have this concept of variational derivatives. The increment in j can be written as variational derivative of j with respect to y at x1 plus epsilon 1 times delta sigma 1 plus variational derivative of j with respect to z at x is equal to x1 plus epsilon 2 times delta sigma 2, where delta sigma 1 is this area between delta y and x-axis, that is this one. Okay, and delta sigma 2 is this area between delta z and x-axis, so this is this one, right? And this epsilon 1 goes to 0 as delta sigma 1 goes to 0, and this epsilon 2 goes to 0 as delta sigma 2 goes to 0, right? So now we are giving this increment, these two increments to y and z respectively. So we have this incremented function, that is y star x is equal to y of x plus delta g of x, and z star x is equal to z of x times delta zx. Okay, and we want these to be our admissible curves. So it means that these two, y star and z star, they must satisfy our extra constraint, extra finite subsidiary condition. So we must have that g of x y star z star is equal to 0. Already y and z were admissible functions, so we already had this g of y x y z is equal to 0. Okay. So now we have this g of x y star z star is equal to 0 and g of x y z is equal to 0. Therefore, g of x y star z star minus g of x y z is equal to 0. Okay, therefore integral g x y star z star minus g x y z dx is equal to 0. So we have this thing, that this integral is equal to 0. Fine. Now this is actually y star is y plus delta y and z star is z plus delta z. So now you can use the Taylors here. Okay. So you will get g x y z plus partial derivative of g with respect to y. Okay. That will be x y z del y. Okay. Plus partial derivative of g with respect to z, x y z del z minus this g x y z. Okay, these two things will cancel, right? So actually you can you have this higher order terms also, right? So if you want to stop at this value of like if you want to, for example, if you have this Taylor's expansion, if you want to write down f of x plus h, you can write it as f of x plus h times f dash x plus h square time by 2 factorial f double dash. Here if you want to stop it here, then you write it here x bar, where x bar is a point lying between x and x plus h, where x bar is a point belongs to x to the open interval x to x plus h, right? Similarly, here I want to stop at this first term. I want to write the Taylor's expansion of this thing, but I want to just write the things up these three terms. So I want to stop at the first term. So I will put bar here, where bar means that I am computing this partial derivatives at some curves which are intermediate to the curve yz and y star z star. See, these two functions together form a curve, right? And I have to compute gy at these curves, right? Gy is the surface and I want to compute the value of that thing at these curves, right? So this bar defines, so basically gy is a function of x, y, z, right? So I have to compute these this function zy and zz at some curves which are intermediate to these two curves, right? So that's why I put the bar. So now I want to find this integral. Okay, so this I assume that this is this gy bar. Okay, this is integral. I am taking this thing is equal to constant in the interval a to b. So I am taking its value as the value at the point x1 plus something which goes to 0 as this if this thing is constant, and I am assuming that that constant is equal to this value of gy at x is equal to x1, then I will be left with a to b delta y, that is delta y dx, that is nothing but delta sigma 1, that is the area between delta y and x axis, right? So and I am calling this because I assume that this value differs from this value by an amount epsilon 1 dash. Okay, the actual value of this thing differs from this value by an amount epsilon 1 dash, which goes to 0 as this area goes to 0, right? Similarly, this thing is gz at x is equal to x1 plus epsilon 2 dash times delta sigma 2, where epsilon 1 dash goes to 0 as delta sigma 1 goes to 0 and epsilon 2 dash goes to 0 as delta sigma 2 goes to 0, right? Now in the theorem, this is the hypothesis that gy at x is equal to x1 and gz at x is equal to x1 simultaneously both cannot be 0, right? So we assume that this, suppose g of z is not equal to 0, you can assume otherwise also, right? And suppose this is not equal to 0, then this is equal to 0, then from here I can compute delta sigma 2 in terms of delta sigma 1. How I can compute? I can just manipulate and take the terms on the other side. I'll get delta sigma 2 in terms of delta sigma 1, which is equal to gy x is equal to x1 upon gz x is equal to x1 plus epsilon dash, where epsilon dash goes to 0 as delta sigma 1 goes to 0. Okay. So now recall what we have. We had this delta j, this definition of increment. This was the definition of increment. Then I have this delta sigma 2 in terms of delta sigma 1, right? I will just substitute the value of delta sigma 2 here. So I will get delta j is equal to, you can do the manipulation. I will get delta j is equal to variational derivative of j with respect to y at x1 minus gy by gz times variational derivative of j with respect to z at the point x1 plus delta sigma 1 plus epsilon, where epsilon goes to 0 as delta sigma 1 goes to 0. Now compare it with the definition of variation of the functional. So you will get that this is your variational, this is your variation of the functional j, right? So you have del j is equal to this thing. Now the necessary condition for the extremum is that this should be equal to 0. Therefore we get this equal to 0, and now this is not equal to 0. So you get this is equal to 0, and x1 is an arbitrary point. So you get that del j by del y, that is the variational derivative of j with respect to y minus gy divided by gz variational derivative of j with respect to z is equal to 0. This is what we got. Okay. So now variational derivative is nothing but the left hand side of the Eilis equation. So this is equal to fy minus dy by dx of fy dash minus gy upon gz times fz minus dy by dx of fz dash is equal to 0. So you just take this thing on right hand side and divide with this with gy. You will get fy minus dy by dx of fy dash divided by gy is equal to fz minus dy by dx of fz dash divided by gz. Okay. So it means that along the curve, this curve, okay, the common value, these values are same. I am calling this is equal to lambda of x. Okay. So then we have, if I am calling this value is equal to lambda of x, then I will get fy minus dy by dx of fy dash is equal to lambda x g of x. So that is fy plus, call it minus lambda of x. Okay. Then you have negative sign here. That will be minus plus lambda of x g of x minus dy by dx of fy dash is equal to 0, and similarly fz plus lambda of x g of x minus dy by dx of fz dash is equal to 0. So these are the Eilis equation in case of finite subsidiary conditions. Okay. You have to note this thing that in here this is not g of x, this is g x y z x y z. Okay. You have to note that otherwise there is no meaning of writing the partial derivative, right? I'm sorry, this was gy. Yeah. Okay. You have to note that in this case the subsidiary condition was this. Okay. There were no y dash and z dash involved. Okay. So what if your subsidiary condition is like this: x y z y dash z dash is equal to 0. Okay. Then also the same thing will work. We have written this in the next slide. You can see. Suppose your subsidiary condition is of this form, then also you have to form another function phi, which is your f plus lambda x times g of x, y, z. Now this contains y dash, z dash, right? So you have to write the Eilis equation for this. Phi y minus dy by dx of phi y dash is equal to 0, and phi z minus dy by dx of phi z dash is equal to 0. Okay, and you have to note this thing, right? In case of this condition, subsidiary condition, that is in case of isoperimetric problems, lambda was a constant. Okay, but in case of finite subsidiary condition, lambda is actually a function of x. So you have to keep this thing in mind while solving the problems. So let us solve one example. So this is the question, that among all the curves lying on the sphere x square plus y square plus z square is equal to a square passing through two given points, this and this, find the one which has the least length. Okay, so this is basically a geodesic problem. Okay, there are many ways of solving a geodesic problem. Okay, so you have a sphere, you have a point, 2 points a and b on the sphere, and these 2 points can be connected by many curves, and we want to find out the curve which is such that it has a minimum length, right? So let the curve be this, right? Then we have to minimize this thing. You know, this is the formula of the length subject to the boundary conditions. So you are given y at a, z at a, y at b, z at b. These are the boundary conditions you are given, right? And you want this condition to be satisfied. So you want x square plus y square plus z square minus a square is equal to 0, right? So your phi will be this thing plus lambda x times this thing, right? Now it's up to you whether you want to write it minus a square or not, because anyway you have to find the derivative. So minus a square will not play any role. So I am writing it as x square plus y square plus z square. But of course you can write x square plus y square plus z square minus a square. Now apply the Eilis equation here. So you'll get phi y minus dy by dx of phi y dash is equal to 0 and phi z minus dy by dx of phi z dash is equal to 0. This will give you this thing 2 by lambda x minus dy by dx of phi dash upon square root of 1 plus y dash square, that is dash square is equal to 0. And these are the two equations. You have to solve these two equations. When you solve, you will have 4 constants plus lambda of x. So those constants are obtained using the boundary conditions and lambda x boundary condition plus this condition, right? So you have 5 conditions and 5 constants, and you get not constants, 5 variables. These are constant, this is a variable. So you can obtain these 5 things using these 5 conditions. So this is how we deal with the problems of finite subsidiary conditions. Thank you.